what I want to talk about is this becoming famous computer, the Harwell Dekatron Computer. This story has got so big now that there's huge amounts I'm not going to cover, I'm afraid, in this. I'm also not going to cover anything hugely technical as well in terms of construction. There are people that know more about this than I do. But really talk about why the machine was designed in the first place and how it managed to survive. I mean, we use the term this charmed life, and really it's the oldest working machine from that period. But to start, I need to take you back to the immediate post-war period. The UK had shared a lot of its technology that was developed pre-war, and same with Europe as well, with the Americans to support the Manhattan Project. So lots of technology and people were shipped over to the US. But the agreement was between Roosevelt and Churchill that information would then be shared after the war. Come the end of the war, we have Truman in the States and Attlee here, and the Americans, quote, lost the agreement. They also then introduced the McMahon Act as well to stop any information being shared. All the information that we'd given and that was developed in the Manhattan Project was then restricted. So we had to start again. Now, there's a period in which the cabinet had pretty well decided that actually that nuclear power and developing a nuclear weapon was beyond the UK, primarily because of finances. But the Foreign Secretary had a meeting with the Americans who basically told him to bugger off, frankly, who came back to the cabinet meeting with this statement, "We're having the damn thing here with a bloody Union Jack on top of it." So a lot of the fundamental research was simply not known then in the UK. So construction began of the Atomic Energy Research Establishment down at Harwell. And this is one of the pictures. Harwell was an RAF base and in full use during the wartime. So John Cockcroft had been asked to actually take charge of this research establishment. He would have rather had a base over in Cambridge. He's very much a Cambridge man. The RAF wouldn't give up any of their RAF bases to the east of the country. So RAF Harwell, down near Oxford, was chosen. There are lots of stories about the actual construction and the taking over of these old wartime buildings. What you can see here is one of the cooling chimneys above, in fact, the second reactor they built there. And just give you one of the funny stories around it. This cooling chimney vented 5.5 tons of air every minute through the reactor, which is in the white building at the bottom, up to the chimney. That's fine, worked perfectly well. However, they discovered they'd actually built almost the largest organ pipe in the UK. And the boom from this, when the air was flowing through it, could be heard 3 counties away. So there were some snags and the rest, but work actually got on really quite well at Harwell. Because it was an RAF base, it had the accommodation for people as well. So very quickly, Harwell developed their first reactor, known as GLEEP, built in 1946 and in 1947. And in fact, only shut down in 1990. One of the problems of not having that fundamental research, I mean, literally things like not knowing what the half-life was of certain radioactive fission products. So Harwell actually employed an awful lot of mathematicians, graduate mathematicians, to come to the exciting world of atomic energy, and were basically sat down with huge sets of tables and mechanical calculators working through endless calculations. I mean, really calculations that would take days. And obviously the possibilities of errors were horrendous. They were helped by these work done in the States of mathematical tables, huge printed books of tables and solved solutions. But they were very expensive and very limited. And in fact, one of the primary uses of the machine, when we come to it, will be to replace these tables. The other thing that happened at the same time was Ericsson, British Ericsson, producing something called the Dekatron tube. Now, the Dekatron tube was developed originally by them for using the telephone systems. I don't think that I believe that actually happened. But the nice benefit of a Dekatron tube is if we send an appropriately shaped pulse in, the discharge will move either to the left or to the right, depending on the pulse, and stay at that value. So if you push in 5 pulses, it will clock round to position 5. If we put another pulse in, it would go to clock position 6. And in fact, you can chain these Dekatron tubes together. So when the least significant one passes 0, it effectively generates the carry to move the second pulse along. Now, Harwell used thousands of these linked to Geiger-Müller tubes for counting radioactive decays. So they understood very well the technology behind using Dekatron tubes. Our designers, which are 3 chaps, Ted Cookie-Arbor, Dick Barnes, and Gurney Thomas, had all come to Harwell from MOD research establishments. They'd all come from Malvern, the war. And Dick Barnes particularly knew about how to build relay-controlled sequence calculators. And he'd been responsible for a lot of the chain home calculator used in early radar. But it's really a chance conversation between the theoretical physics group and the electronics group that, well, actually, we ought to be able to design a solution to print these tables. And like everybody else at the time, they'd been across to Cambridge and they'd seen the EDSAC computer working. EDSAC was rather out of their league, but they felt they could design a machine to solve their immediate problems. So the next job was to actually make a case for building this machine to the head of the station, John Cockcroft, and the head of theoretical physics at Harwell, which is Klaus Fuchs. Now, there are other fun stories about this. The Ted Cookie-Arbor and Dick Barnes typically would expect a real knockabout session with Cockcroft and Fuchs. Be questioned and interrogated and made to justify their design. This meeting went very, very quietly. And after something like 20 minutes, Cockcroft said, well, it sounds like a good idea. Why don't you get on and do it? Our engineers only found out months, if not years later, that it was only that morning that Cockcroft had been told, had admitted he'd been spying for the Russians. So it was obviously a somewhat tense meeting. But they started the design of the machine in early 1950. Now, this photograph is almost the passport photograph for the machine. There are very few pictures taken of the machine at Harwell itself, which is a great shame, but this is one of them that was published. And they completed the machine in 1951 with what's known as 2 store groups. Now, you can see those 2 panels on the left-hand side of the machine with rows of Dekatron tubes. And that was enough to actually prove that the machine worked. And there are stories of the mathematicians getting to grips with the programming for the machine, actually really very quickly. The important thing we'll come to as well, the machine was incredibly reliable. But to give you an idea of the programming challenge for the machine. This is effectively the complete instruction set. Now, if I look at the arithmetic orders on the right, we can add one store to another, perfectly reasonable, subtract one store, and actually in hardware, multiply and divide locations. That's pretty unusual. In terms of control, the only jumping is to jump to a different program source, which is a different paper tape reader. Now, the machine actually could operate as a purely stored program computer. So we could transfer the entire program into the store and run from the store. But typically with a limited store, which you need for variables, we would run from paper tape. So we can do jumps to a new source, which is to jump to a different paper tape reader. We can search for particular blocks on particular readers, and we can print the accumulator, we can stop, and we can do tests for a positive or negative against any of the stores. But typically, a program would look like this. In the first block there, the Bootstrap, we have punched paper tape in tape reader 1. And the instructions we're going to do here is to clear a set of stores. Then there are 3 add instructions. Oh, and actually they're adding from a different reader, which is rather nice. Then we're searching for block 1 on tape 2. And effectively, this is the control, this is the jump to a subroutine. We're actually going to go and jump out to that extra bit of code. Now, subroutines, obviously, we'll call more than once. And the very smallest subroutine that we can do on the Harwell is that little loop of paper tape. So if we imagine that paper tape's probably a little bit small, if that was several meters of tape, it might be a subroutine that does a square root. And we can call out to that paper tape reader. It will start reading commands from that paper tape until it transfers back to the main program, almost like the return from a subroutine. One of the issues with that is these are mechanical paper tape readers. A small loop like that, by the time it's gone around about 10, 20 times, the paper tape punch reader will have punched its own holes in the tape. So it was quite typical to use Mylar tapes if it was a routine that we needed to keep and execute repeatedly. But the machine worked very well. Ted Cook-Yarborough published some figures as well. Ted Cook-Yarborough makes the point, a slow computer can only justify its existence. This is a very slow computer. Multiplication can take anything from 10 to 16 seconds. But it, as Ted Cook-Yarborough makes the point, capable of running unattended for long periods. And one of the famous stories is that the machine was actually set to run with a series of problems just before the Christmas break, and was still running quite happily on its own when everyone came back to work in the new year. So 55% of the total running time is pretty amazing for a machine at that time. One of the other stories about the machine at Harwell is Bart Fossey. Now, Bart Fossey is the chap on the left. He was an excellent mathematician and very, very experienced with a hand calculator, mechanical calculator, like a Brunsviga. The story is, from Jack Howlett, that Bart Fossey sat down with the machine and attempted to race, and apparently kept up for about half an hour, working flat out, but had to retire exhausted, and the machine carried on. But that's a reasonable guide to the speed of the machine. It's about as fast as a good hand calculator Brunsviga operator. But time moves on, and the machine was used regularly primarily for the production of tables, mathematical tables. But by 1957, it was time for the machine to be retired. Harwell had built a transistorized compute machine in 1955 called the CADET. And by this stage, they were buying commercial off-the-shelf computers, the BTM machine for anti-mercury, and had access to their colleagues down the road at AERE, who had fairly spectacular machines at the time, a Stretch and an Atlas machine. But such was the regard for the machine, really, by everybody that was involved in the design and the use of the machine, that they declared a competition in 1957. Competition to any college or university, or potentially even school, that would put together a case for having the machine and how they would actually use it. John Hammersley was at the Oxford Mathematical Institute, but on secondment to Harwell at the time. It was obviously quite successful because there were 30 submissions to Harwell for the machine, and that was brought down to a short list of 9. And again, the guys at Harwell remember the delegations from schools and colleges arriving. Wolverhampton bought their mayor, complete with chains of office as well. But the winner was Wolverhampton Staffordshire College of Technology. Now, this becomes very, very useful for us as a museum. One of the people in charge of the machine at Wolverhampton was a chap called Cecil Ramsbottom. And Cecil Ramsbottom got every bit of news in the machine about the machine in the press as quickly as he could, which is wonderful for us because we have access to all of those cuttings. And Wolverhampton were really quite proud of themselves for winning the machine. Somewhat slightly odd comments. Besides being available for instruction, the computer will also be available for hire to industry and commerce in the Midlands. And they did come true of that. The next statement, it can, for instance, work out wage calculations much more quickly than human beings. That is absolutely not the case. Any experienced bookkeeper at the time running payroll would have whipped through those a payroll compared with the machine. And of course, the only commercially, let's say, comparable machine that the college might have bought was £50,000 and more. Now, at this point, it was known as the Harwell computer, which they run. When it arrived at Wolverhampton, it became known as the Which computer. It's a bit tortuous, but the Wolverhampton Instrument for Teaching Computing from Harwell. And again, much more, lots more press coverage as well. And I think these are, this is an example from the Birmingham Post. It did allow Wolverhampton to actually start the first undergraduate course in computer technology in 1965, which is really, really quite impressive. They also produced a book about the machine as well, although titled An Introduction to Computing, with a nice little graphic of core memory on the front. It is primarily about the Which computer, the Harwell computer. The other promise that Wolverhampton did, or said, was to share the machine with local schools. And indeed they did. They ran classes for local schools and bringing in sixth form students and fifth form students to actually use the machine. And again, I think it's Cecil Ramsbottom, who you can just see his face holding paper tape, used every opportunity he could to get the machine in the press and talked about. One of the really iconic pictures of the machine is this next one. And it's known as the Chubb Key Problem. Chubb, the locksmith company, at the time were in Willenhall, not far from Wolverhampton. And one of the problems that Chubb had got is when making keys, certain patterns are too weak to be of use practically. And they commissioned Wolverhampton to actually write a program for them to actually list all the solutions and the pin sizes in these mortise keys. Now, this picture on the left, on the right rather, the student next to the machine is a chap called Peter Burden, and one of the masters next to him is Frank Hawley. Now, if any of you've seen the book that the museum produced about the machine, Delwyn and I tried to reconstruct that picture fairly hopelessly on the front cover. Now, you can see one of the loops of paper tape, which they are seriously studying here. When they actually ran the program for Chubb, and it took over 10 days for it from start to finish, those paper tape loops were stretched from one side of the machine, one side of the room to another, with about 30 or 40 repetitions of code on the paper tapes. But famous to it, it actually did the job and worked perfectly. So they did actually honour their commitment to local industry. I'm very proud about. Of course, by 1973, Wolverhampton now are in a position to buy their own machines, and they actually bought an ICL 1900 machine. But again, Cecil Ramsbottom gets his picture, the retirement in the paper again, which the computer earns part retirement. The other thing that's famously that Cecil Ramsbottom did was contact the Guinness Book of Records and had the machine listed as the world's most durable computer. It's a slightly odd term, but that was in 1973. I'll come on to it later, but we've since been back to the Guinness Book of Records, and the machine, the record is still valid, and it's still an entry in their book. The second retirement took the machine to the old Birmingham Museum of Science and Industry. If anybody knows the museum was completely fantastic, and everything a museum should be. It was a huge rabbit warren. This is just the front. It went a long way back in Birmingham, in Newell Street, back to following down canals, and it was quite a fantastic place. The machine was actually put on display. To my knowledge, it was never actually run, and we do have a copy of a letter from the museum back to Harwell, asking if Harwell could actually help and get the machine working again on display. Harwell, I'm afraid, actually were unable to help. They're really too busy with everything else. But the machine stayed on display until really 1997. Now, I spent pretty well every Saturday afternoon as a teenager at Birmingham Museum of Science and Industry, and actually remember it there. There were a couple of the similar simple machines, relay-based box and geese machines, and so on. Birmingham Science Museum sadly was closed and replaced by some god-awful thing called a think tank. The machine itself was sent to their collection centre, again in Birmingham city centre. Now, this photograph is one from a series of photographs I was looking at, and I was looking for a completely different machine. A colleague of mine in the Computer Conservation Society was looking for a BTM machine and had been to the collection centre and took a lot of random photographs as well as the machine he was interested in. Some years later, I was reviewing those photographs and saw this one and thought, actually, I recognise that. That front panel there, which you can just see in the middle, I recognise that from the Harwell machine. And in fact, we went back, by the time I was looking at these pictures as well, Birmingham had moved its collection centre to a wonderful new location just outside the city centre. And we made a visit to that centre on November 2008. And you can just see right at the back, there are 3 semicircular covers, and that's part of the Harwell machine. Everything else was in front of it. we had to dig everything else in this way. This is an Orion for anti-Orion console at the front. There's a huge Bryant disk drive behind it, which, believe me, weighs an up to ton. Various other machines behind it, but eventually we got to the back of the machine, got to the back of the collection center warehouse, and found the machine, and found what we thought was pretty well most of the computer. And of course, we decided that, well, actually, if we've found enough, is it a candidate to be restored to working order? We came back and started looking at some of the questions for this restoration. Have we found all the hardware, or have we found sufficient hardware? We might have some bits missing, but have we found enough? Do we have any access at all to manuals or diagrams? At that stage, we didn't have anything at all. Are the original designers or users or programmers are able to help, or indeed still with us? And do we have everything we need to restore a machine like this? People, engineers to actually do it with the time, the skills appropriate to this machine, the finance, can we afford to do this? And probably the biggest problem is space. Do we have space to actually do this? And if we restored the machine, what would be the eventual plan for the computer? And should we attempt the project? Now, on one of the trips back to Birmingham, we found this wonderful pallet high up on the shelf. And we literally had one of my colleagues almost strapped to the front of a forklift truck, being driven up and down various aisles in this storage center, getting higher and higher and higher, looking for anything that looked likely, and then found this box. Now, we can't see all of it in here, but there are replacement tubes. There are samples of paper tape. But when we started to dig in this box, one of the things we found was the entire description of the computer, a precise sort of circuit operation, circuit diagrams, the theory behind the machine, really quite fantastic. I mean, beautifully produced. But the theory of operation and the circuit diagrams convinced us that actually this was a possibility. The other nice thing at the time, again, a chance conversation at the British Computer Society, put us in touch with Dick Yarborough, who's the sort of slightly frail gentleman on the left in the top picture, and Dick Barnes, who's in the middle. That's my colleague Tony Fraser at the right, on the right. We went down in 2009 to see Ted Cook Yarborough and Dick Barnes. The amazing thing is they had each kept a scrapbook of newspaper cuttings and articles about the computer. So we spent much of our time, I think you can see there's a picture of me and Dick Barnes comparing our cuttings. They were absolutely thrilled that we could do this and were incredibly supportive. So we formed a new working party and a proposal to the Computer Conservation Society of 2009, and then a very careful proposal to the Birmingham Museum's Collection Centre. It's difficult to know how a museum will react to a request to have the machine and restore the machine to working order. There are very few computer specialists at museums, but Birmingham were actually terrific. They were really thrilled with the idea. We made the proposal in May, and 2 months later, they came back and said, yes, you can have the machine and you can restore the machine. Another visit back to Birmingham, of course, just looking, making sure we found everything. And luckily, the Computer Conservation Society awarded us some funds to move the machine to the TNMOC. And it arrived on 3rd of September, 2009. I'm not going to cover a huge amount about the restoration process. it was very well engineered and designed at Harwell. It had obviously suffered in the various moves, and well, obviously it was working at Wolverhampton. By the time it went from Wolverhampton into Birmingham Museum, and then into Collection Centre, then to another collection centre, and then eventually to us, there were problems. The usual things about rubber-covered wires and damaged wires and broken connectors and so on. Actually, remarkably few component failures. The other thing that was had been neglected, I think, is the maintenance of the relays in the computer. It uses standard post office relays, which Strowger equipment was absolutely full of them. But luckily, anybody that's worked professionally on Strowger equipment knows how to realign the contacts on relays and how to set relays up. So we were very lucky to have that help. Also, of course, we have the benefit of modern test equipment. This picture, it was the back of Delwyn's head, who was the primary engineer on the machine, and Dick Barnes coming to visit the machine. I think Dick had a wonderful day, actually. But very quickly, the machine was actually restored to working order. One thing that we wanted to do particularly is something called the Reboot Day. Now, the Reboot Day, that's me sitting in the middle in the suit. Ted Cook-Yarborough, the original designer, is on the right. Next to him, Dick Barnes, again from Harwell, me in the middle. Bart Fossey next along, the mathematician who took part in the race. And then Peter Burden. Peter Burden was the student we saw standing next to the machine and wrote much of the Chubb, the program to solve Chubb's problems. Peter Burden was at the time a sixth form student waiting to go off to Cambridge to read maths, which he did. His first job when he came back out of university after he graduated was back at Wolverhampton, actually using the machine again and teaching with the machine. So it's really nice to have all these people together. Ted Cook-Yarborough was very frail by this stage. His family came along with him and said that he would have crawled across hot coals to get to the machine on this particular day. And it was fantastic having them all with us. I'm sad to say that of the four there, Ted Cook-Yarborough, Dick Barnes, Bart Fossey, and Peter Burden, and none of them are no longer with us, which is a great shame. But this was a fantastic day. We had Bart Fossey recreate the race, him using a mechanical Brunswick calculator. The press coverage was quite phenomenal. There's a video on YouTube. The machine today is obviously on display at the museum. It's still very reliable. It's a perfect machine for demonstrating to students how computers work. We can single-step code through the machine, and if we're single-stepping code, we can actually read on the Dekatron tubes the value in the accumulator, the value in the stores. So we can click the single-step button and actually see individual operations taking place. And this makes such a difference when we're actually trying to explain how machines of this type work. There's also a sort of, I think for the students, there's a sort of a slight hint of, or apparent slight hint of danger when they're using this big machine. I mean, they're obviously not particularly close to it, but it's an exciting machine to use. Now, I've whipped through this fairly quickly, but what I wanted to point out to you is the information that you can search. If you search for Harwell Dekatron or oldest working digital computer, there's a lot of information about the machine. The Computer Conservation Society website as well has a great deal. If you search for Harwell Dekatron Tube on YouTube, you'll see the video of the reboot day. And of course, there's a lot of information on the museum website. And you can also, advert coming, buy the book about the museum, about the computer as well, which has lots of the pictures you've seen here and a lot more technical information about the restoration project itself and how the machine works. Now, I whipped through that, I must say, very quickly, but I wanted to give us plenty of time for questions. And if there were any or are any.
I've got one, Sheridan here. You refer to it as the world's oldest working computer, but it's important to say, I think, it's the world's oldest original working computer, because there are, Manchester babies are older than that and it works, but it's a replica.
Oh, yeah, no, absolutely. I mean, the official title is the oldest extant working computer. There is another machine which we had in Japan, the Facom machine. We had a little bit of a battle with at one point. But no, the machine is the oldest extant original working computer. Thank you, Sheridan.
Just to say something about the potential use of the Decatrons, as they were manufactured by ETL, latterly, I think, Plessy Telecoms at Beeston, some years later. There is a rumour that they were used in telephone switching. There is a patent, I think, 1952 or something like that, on the use of Dekatron tubes in telephone switching. But yeah, I've an unsubstantiated story, and I've been trying to find out the truth of it or not, but that they were used in a switch in Coventry Telephone Exchange, and they suffered a problem which we have from time to time with the witch at TNMOC. Whereas if at a certain time of day, on a sunny day, the light would come in through a fan-like window and would cause this Decatrons to overstep, as they were slightly more ionised than they should be at that particular point. That's the story. The truth of it is probably somewhere, it's lost in the mist of time.
Yeah, I mean, obviously, British Ericsson obviously developed the machine for use in telecoms equipment and telephone switches. I didn't know that actually got that far at all, which is I think really they managed to sell enough as counting tubes for the rest of the world. One thing about the machine, though, is that the Royal Aircraft Establishment down in Farnborough had been to see the machine, were planning to build a copy of the machine themselves. They were going to keep the Dekatron tubes for storage, but replace the relays with electronic control. Royal Aircraft Establishment were persuaded to get into bed with Rakel to do this, and the machine was going to be known as Rascal, a machine that would actually be in production and sold. I think by the time that the bureaucracy at Royal Aircraft Establishment and Rakel had got their act together, it was too late. The machine wasn't actually, there were readily available machines to buy instead, which is a shame. But of course, Dekatron tubes went on for a huge amount of use, quite phenomenal. Even if these days, most of that use is on eBay, people building clocks, which is a shame, but yeah.
They are very low power consumption as well.
No, absolutely. Absolutely. And well, Peter, you know this, being able to demonstrate a machine where you can actually look at the store, it's just really quite amazing, isn't it? So, yeah.
Well, Sheridan's the man for that. He's got more patience than I do.
And there was a question about, I saw a message pop up about, can you program the machine? Yes, absolutely you can. There's lots of information on the web, everything you need. I've lost track. We several of us started an emulator for the machine and didn't get terribly far. I didn't get terribly far. I know Bob Jones did at one point as well. But yeah, absolutely, we would be more than chuffed to bring along a program. You'll have to sit and punch it, but we can help you punch it onto paper tape and then try it through the museum. And I'd be thrilled to bits.
There's also a question as to which version of the Dekatron is being used. Is it a GS10?
more people technically know about it. I know the history. I'm the historian. I know there are different tubes because the early tubes have different glows and they're more readable.
Yes, we do use two sorts, don't we?
Yeah. But actually, it's remarkable. I think the tubes that I hear fail are the so-called trigger tube. And then the odd high-value resistor goes out of spec or a capacitor dies, but that's something you would typically expect. But the Dekatrons themselves, apart from becoming what's called sticky, in that although we provide the shaped pulses in to move the discharge from, say, pin 1 to pin 2, it doesn't. So one of the routines we have is to exercise the machine just to drive that round and actually just to keep them actually moving. But remarkably reliable.
I think from memory, one of the failure points is the 1 mega ohm wire wound resistors used in the anode power supply.
Actually, I did mention, when I put the slide up about Ted Cook saying it was allowing for a 5-week period of damage, I think he said in the slide. Famously, Ted Cook, a big chap in charge of electronics by that stage, research at Harwell, was climbing up on the machine to lift one of the stores up, lifted the store off, and then dropped it, which could have made a terrible mess. Talking separately to the other 2 engineers and the team, who then quietly giggled and said, just thank God it wasn't us that did it, but if the boss did it, then that's fine.
It's also worth mentioning, I think, that when it was at Wolverhampton, it was modified. It had the extra store rack put on, didn't it? And the sort of printer driver on the connectors on one of the cans.
Yeah, the store rack had been provided, and there's this awful sort of bit of Dexion on the top left of the machine, which sort of sits there. And if anyone's used the machine more than once, they almost certainly will have cracked their head open on that bit of Dexion as you walk around the machine. But yes, one of the things is as the machine was designed for printing tables, the actual format of which it would actually print is pretty limited. Some work was done at Wolverhampton with a sort of patch panel top right to actually alter that print layout. I don't think we've ever quite got to the bottom of that.
Mark's asked a question as to whether there were spares available from the University of Wolverhampton when it became university.
No, they handed the whole thing across to the museum. It's a real shame. It was on display. I can say, well, I have the curator at Birmingham at the time, a chap called Mike Constable, and he'd written to Harwell to say, look, he would like to have the machine display working, which actually was pretty unusual for the time for museums. But Harwell had to decline to say, we just don't have time. And it's a shame, but it enthused people like me, so that's fair enough. Yeah.
Kevin, did you ever see actually in its location the portrait of a dead witch?
Oh yes, no, that was next to it. See, this is the story. The story has got so big. One of the things that was a chap called John Yeardon. John Yeardon painted an oil picture called Portrait of a Dead Witch, and that was or the sketches for it were done at Birmingham Museum and was actually put on display for a short time. Now, we did quite a bit of work a couple of years ago now and managed, particularly Stephen Fleming, and managed to find this picture, oil painting. And this thing's it's pretty big. It's about sort of 6 foot by 4 foot, something like that. On the museum, on the wall of a cafe in Manchester, the Jam Cafe in Manchester. The owner of the cafe thought it looked quite nice and quite pretty, but had no idea what it was. So we persuaded her to lend us that picture temporarily, that painting. Also then got in touch with the artist, John Reardon, who then commissioned a new picture Sheridan, I can't remember what it's called, but basically it's a portrait of a restored witch, I think.
Yes, basically, yeah.
Which is really quite incredible. The stories behind the machine are phenomenal. One, I talked about Wolverhampton starting an undergraduate course. There was something like 10 students on that undergraduate course. On one occasion at the museum, all 10 students came back to the museum to see the machine. And they'd all kept in touch because, in fact, IBM visited the college to see what all this was about, computer education, offered them all jobs. The bulk of them went off to work for IBM. And this was their retirement, and almost like a retirement treat, to come back to the museum to see the machine working.
Yeah, we took a picture of them side by side, the old and the new, haven't we?
I think there's a sort of, going back to the museums, it's almost like if you build it, they will come. The fact that if you put this on display, the stories that come out, it's incredible. I gave this sort of presentation to something called the New Commons Society 2 weeks ago. And one of the audience there was another one of the students that had used the machine prior to going up to Cambridge and was part of the Chubb program as well. So we learn more and more and more.
Okay.
I hope that was useful or interesting.
Definitely.
Thank you all very much for joining in.
A very good talk. Thank you.